Hello, this is Rui Chen. This is my final presentation. It is called a system architecture for running big data workflow in the cloud. The outline for this paper is like, first the author talk about introduction in the related fields, and then we talk about the main challenges in using cloud in scientific workflow management systems, and then we propose a system architecture, and at last it did a case study and through the conclusion. So nowadays, everybody is talking about scientific workflow. So what is actually scientific workflow? Scientific workflow can be thought of as data pipelines consisting of heterogeneous software components connected to one another and to some input data products. And a scientific workflow management system is a software system that allows domain scientists to design, store, and execute scientific workflows to solve their domain problems. And there are three advantages to use cloud in scientific workflow management systems. First, it will facilitate better resource utilization because cloud services are only used on needed basis. Second, they will help domain scientists to achieve better trade-off between performance and the cost of data analysis. And third, it will enable scalability on demand when more data need to be processed by a workflow than originally expected, or when more scientists need to use a collaborative scientific workflow management systems concurrently. So there are four main challenges in using cloud in scientific workflow management systems. First is called the platform's heterogeneity challenge. The process of connecting to a particular cloud is defined by the cloud provider and is generally different for different vendors, so connecting to the cloud is challenging. And the interfaces exposed by various providers to provision cloud resources are also different, so resource provisioning is challenging too, and bundling, uploading, and registering images also vary by different cloud platforms, so it's challenging to create merging images. And then oftentimes, after running a workflow in the cloud, the user may want to switch to another cloud. So it's challenging to migrate a workflow between cloud platforms. And the second challenge is called resource selection challenge. Running a workflow in the cloud always involves a choice of the number and types of virtual machines to execute a workflow. So it's challenging to select the resources. And the third is called the resource volatility challenge. So basically persisting output data products, registering new components or data products, cataloging virtual resources, and setting up the environment are challenging. And the last is called the distributed computing challenging. It's challenging to pass big data products to consumer components, and logging and the workflow monitoring is challenging too, and it's challenging to keep the provenance collection. So the author then proposed a system architecture, and he named it the data view system. So basically, the system contains four different layers. First is presentation layer, which contains the client-side part of the system. Second is called the workflow management layer, which contains subsystems orchestrating the process of the data flow. And third is called the task management system, the task management layer, which contains modules that ensure successful execution of individual tasks in the cloud. And the fourth is the infrastructure layer, which contains the underlying IaaS cloud platforms where workflows are dispatched. So this is a picture which illustrates the details within the system architecture. As you can tell from the picture, you got a presentation layer, you got a workflow management layer, you got a task management layer, and you got the infrastructure layer. And basically, the architecture consists of workflow design configuration subsystem and workflow engine subsystem, workflow monitoring subsystem, provenance management subsystem, task management subsystem, data products management subsystem, and some other subsystems as well. So basically, The workflow design configuration subsystem provides intuitive way for users to design workflows as well as specify workflow configuration. Workflow engine subsystem is a central subsystem that enables workflow execution. Workflow monitoring subsystem keeps track of the status of individual components, and data product management subsystem stores all data products used in workflows. And the provenance management subsystem is responsible for storing, browsing, and querying workflow provenance. And the cloud resource management subsystem plays a key role in provisioning, cataloging, configuring, and terminating virtual resources in the cloud. So this is a picture that illustrates the details within the workflow engine subsystem. As I mentioned before, the workflow engine subsystem is a central subsystem. And as you can tell from this picture, it consists of the translator module, the data flow management module, the workflow configuration management module, the EBS volume management module, the profile tracker module, the runtime behavior and analytics module, and the provenance collector module, and something else. So the translator module is responsible for producing executable representations of workflows from specifications written in our XML-based SWL language. And the workflow management module captures required cloud-related settings to run the workflow. And data flow management module moves data products within a virtual machine to ensure that every component receives each of its input data products as soon as it is produced by an upstream component. The EBS volume management module leverages elastic block storage volumes to reduce workflow running time. The profile tracker module captures execution times of each component. The provenance collector captures data derivation history in appropriate format, and the runtime behavior analytics module uses runtime performance contests of each workflow components to predict its running time and the overall workflow running time and cost. So this is a picture that illustrates details within the cloud resource management module. As you can tell from the picture, there is VM provisioning module, there is EBS board volume provisioning module, there is machine imagery management module, there is snapshot management module, and something else. And then the author implemented the system and through the case study. So this is a screenshot of the driving skill assessment report produced by the author's big data workflow in the data view system. As you can tell, for each individual driver, you got the assessment for abrupt acceleration and braking, this metric, and the assessment for acceleration smoothness, the assessment for smooth braking on turns, and at last you got an overall grade assessment that is either pass or fail. So based on this assessment, the author threw us the results of his implementation case study. So the first picture shows the running big data workflow in the cloud using different number of slave nodes, and the black column is using traditional file transfer, and the gray column is used proposed volume movement techniques. As you can tell, for the same number of slave nodes, the proposed volume movement technique costs less time than the traditional file transfer. And this figure shows the data movement technique used. So when you move the 3 GB data sets between the two slave nodes, the movement time it consumes. If you use the regular traditional file transfer technique, and you got this column when you use the proposed volume movement technique. As you can tell from this picture, obviously, if you use the proposed volume movement technique, it costs much less time. So, in this paper, first, the author identified 4 key challenges of running big data workflows in the cloud. And second, The author proposed a generic implementation-independent system architecture that provides guidance for different implementations of big data-oriented scientific workflow management systems in the cloud and address most of the challenges discussed. At last, the author implemented the data view system that delivers a specific implementation of the author's architecture and run a big data workflow to validate that the system architecture is platform independent. So this is my final presentation. The acknowledgement to Andrew and to Professor Xiong Lu. So thank you.